Buenos dias. Let's take a look at a number that satisfies the conditions of this problem. Let's say 5 squared. It's a perfect square. Okay, that's equal to 25. And that's certainly equal to a multiple of 3 plus 1. So that's equal to what? 3 times 8 plus 1. Now what this is a special case of what the problem is trying to convey. Notice that we would be talking about a plus 1 here. A plus 1 equals 9. Again, y'all, I'm not reading this off for you, but if 3n plus 1 is a perfect square, which we have right here, show that n plus 1 is the sum of 3 perfect squares. Well, notice that's the case here because you can write 9 as 2 squared plus 2 squared plus 1. And that seems a little trivial, but it's true nonetheless, so we'll write 1 squared just to make sure we conveyed the... See there, folks? So there you go. That does satisfy this condition, the sum of 3 perfect squares, albeit indistinct. Okay? Now, another way to write this, folks, another way to write this would be, if you prefer, I don't know if it's particularly useful here, but this condition would be the same thing as saying, let me write it to the left here, a squared, where a is an integer, is congruent to 1. This is the modular arithmetic way of writing this. I don't think it's particularly helpful, maybe so, but mod 3. I think being explicit kind of helps you see what's going on a little bit better here. Okay, but this statement right here is absolutely equivalent to this statement. Okay, now it's clear that a is not a multiple of 3. All right, so that means if a squared is not a multiple of 3, there is no way a could be a multiple of 3, or it would contradict this original statement. Now, so that means that a itself, not a squared, has to be 1 less than a multiple of 3 or 1 more than a multiple of 3. For example, let's see here. A simple example would be 15, right? Okay, is a multiple of 3, right? But then 3 times 5 plus 1 would be the number just to the right of 15. And then 3 times 5 minus 1. Now there's another way to do this, but the algebra would be a little more messy. So folks, again, this is a multiple of 3, and you have a non-multiple of 3 to the right, immediately to the right, and immediately to the left. You could do 3x plus 2, but I think the algebra gets a little more raunchy that way. So, but anyway, let's carry on. I've already written down most of the algebra here for you, so it doesn't require a whole lot of explanation. I wrote 3n plus 1 is 3x plus or minus 1 quantity squared, which is consistent with the statements right up here. All right. Now, so we're interested in n plus 1 ultimately, so we're trying to get n isolated, which is what this statement is. We subtract 1 and divide by 3. Now, when you expand this out, you get 9x squared plus 6x. All right, but if you divide that by 3, that's where this comes from. Okay, that's where this comes from. And notice you would have 1/3 minus 1/3, so that goes away. So that's how this happens. Okay, now we are interested in n plus 1. We're trying to show that n plus 1 is the sum of 3 perfect squares, right? So we just physically force it in there. So you have n plus 1 is equal to this. And all this algebra is very, very straightforward here. This would actually be, just kind of wrote here, x squared plus x squared. So that's 2 squares. They're the same squares, but nobody said they had to be distinct. And this is plus x plus or minus. You know, the plus or minus, you can't get rid of it just because of what we talked about earlier. All right. So that's it, folks. That gets the job done. We've written it as 3 squares, right? This is a square, and this is also a square, right? So it does sum up to 3 squares. And we saw that in the original example, you know, it was the same 2 numbers, right? 2 squared plus 2 squared. I do have another example here for you. n would be 40 in this case, right? N would be equal to 40. That's clear. 11 squared is 121, so 3 times 40, 3 times 40 plus 1 is 121. All right, and right here, 40 plus 1 is 41, but notice that's consecutive squares, or well, not consecutive squares, but this is what, 16 plus 16 plus 9. And again, it's exactly what you would anticipate here. It's either going to be one higher or one lower, okay? Let's see, plus 9. Now, I'm sure everybody trusts 32 plus 9 is 41, right? Another example would be, let's do maybe 255. What is that? 3 times 85 is 255 plus 1. That's equal to 16 squared, right, folks? 16 squared being 256. I won't write that down. But notice here what's going on here. Our n plus 1 would be 86. So you see 85 plus 1 equals to 86. Now let's see if we can dream up the squares here. You can, when the numbers are this small, you can just pretty much guess them, or you can look at the form, but this looks like it's equal to what, 5 squared? Yeah, 5 squared plus 5 squared. That gives you 50, right? But we still need 36, so that would be plus 6 squared. So you see, that was on the high side. All right, remember, the form is plus or minus. Here, this one was on the minus side, but with the plus sign here, this would be on the so-called high side. But that's equal to what, 25 plus 25 plus 36. There you have it, folks. But again, we completed the problem right up here at this circled statement. But we started with a little bit of numerical evidence and then worked a few other cases. But anyway, thank you for viewing.